Yeah, so I'll be discussing about the work which is squashed quantum non-Markovianity. If there are any questions at any point of time, please feel free to interrupt. As you may see, the slides number is just 21. We have ample amount of time for discussion. This work is done in collaboration with Rajiv Gangwar, who is PhD student at Aizer Mohali. Tanmoy Pandit, he's doing his postdoc with Giulio Kiribella. Vikas, he's in Hong Kong. Me and Manavendra Nath Vera, who is at Aizer Mohali. So the details can be found in this archive link, which we posted recently. So the main motivation for this work is we are looking at the quantum correlations in state. So there is non-Markovianity also discussed, or Markovianity also discussed for the dynamics. And then we also have correlations which are in states. I'll be limiting myself to the states. I won't be going to the dynamical picture or non-Markovianity there. It is sort of, they are related, however, it is different. So now, what is the motivation? So there has been long quest to understand possible quantum correlations. I mean, it started right around the time when there was this EPR paper, the question raised by Einstein whether the quantum mechanics, like if the theory is compatible or not with the reality. Now, there are different examples of quantum correlations. For example, we have entanglement, quantum non-locality, steering, unextendability, and then so many of these are also for bipartite or multipartite settings. And then we have quantum non-Markovianity or Markovianity. Now, why the study of these quantum correlations are important is because if, like, from the application side, let's say if we want to do teleportation, then we will need entanglement as resource there, right? So if we want to do device independent quantum key distribution, we'll need non-locality. So if we understand quantum correlations better, we may have their applications. And of course, to understand quantum theory or from the fundamental aspects as well, for those who are not interested in applications of it. Then one of the way to understand these correlations, like it has been formulated in the resource theoretic framework. What is resource theory? We'll come to it during the talk. So before going to what quantum non-Markovianity or quantum Markovian states are, let us just recall some of the entropic measures. So the first one being quantum von Neumann entropy. It is defined for any density operator. So density operator represents the state of a quantum system. So if the state of a quantum system is uh, denoted by rho A, then the density von Neumann entropy of system A is given as minus trace of rho log rho. Then we have quantum mutual information for bipartite state. So whenever we have two systems in a joint state, then we can define quantum mutual information. So it is correlation between system A and C as sum of von Neumann entropy of system A. Sorry, von Neumann. It is sum of it is von Neumann entropy of system A plus von Neumann entropy of system B minus von Neumann entropy of the joint state AB. So we subtract it from this. Yeah, sorry, it should be C here and B should be C here. So there is a typo. Now the quantum conditional mutual information, it is a tripartite correlation measure for a state, tripartite state rho ABC. It is can be so here it is conditioned on B. If this function is symmetric if I interchange A and C. The value of function won't change if I interchange A or C. However, that is not the case. I cannot replace C with B. So now this conditional mutual information, it is defined as mutual information of AB with C minus subtracting the mutual information between B and C. And it can also be written as sum and difference of von Neumann entropies. Now for any state, any quantum state, this quantity is always non-negative. So the following statements are equivalent. There are other statements also which are equivalent, but we'll focus for now just on three. Uh, no, it is A colon. It is mutual information between AC conditioned on B. It should be read as mutual information between A and C conditioned on B. Yes, this is single system AB here, and then yeah. Yes. Yeah, so now the following statements are equivalent. That is non-negativity of quantum conditional mutual information for arbitrary quantum states. A strong subadditivity of von Neumann entropy. So strong subadditivity means, so we have this von Neumann entropy plus this is greater than equal to this tripartite von Neumann entropy, von Neumann entropy of this tripartite system plus von Neumann entropy of B. And then monotonicity of quantum relative entropy for quantum states under the action of quantum channels. It means that the quantum relative non-entropy, it is another distinguishability measure between quantum states. It is monotone under the action of quantum channels. Okay, that is, it is non-decreasing. I mean, if I apply, so here, if I apply quantum channel and then want to distinguish between two states, it will be non-decreasing. Like, we cannot do better, we cannot distinguish them better. So now we come to the title or the main focus of this talk, which is, let us define first quantum Markov state. So what do we mean by quantum Markov state? It is a tripartite quantum state, rho ABC. I mean, we will call it quantum Markov state, whereas this represents, so A, B, C in this order. We can replace, we can swap A and C, but B has to be in between. If its quantum conditional mutual information is vanishing, that is, the conditional mutual information of AC, mutual information of AC conditioned on B is equal to 0, then we say that the state, tripartite state, is quantum Markov state. And this definition is motivated or is quantum analog of classical Markov chain. So even in classical case, if you have tripartite probability distribution Pxyz, in that case the conditional mutual information of the mutual information of x with z conditioned on y is equal to 0. And here we are taking quantum conditional mutual information to be equal to 0. So this is analog of it. Now in classical case, when we have this tripartite probability distribution, you also have marginals which are, you can, that also gives you conditional probability and just probability. Now, if you have probability vector, then the quantum analog of it is density operator. But since it also gives you conditional probability, another analog that comes is when we say about quantum Markov dynamics, which we are not going to discuss here. We are taking analog in the state picture, not in the dynamical picture. However, from there, I mean, when you have Markov chain, you also have Markov process. You can also have quantum Markov process. We are limiting ourselves to the state. That is what I had mentioned. It's quantum analog of classical Markov chain. Now, if conditional mutual information is strictly positive, it cannot be negative. It can be either greater than equal to 0. If it is equal to 0, it is Markov state. If it is strictly positive, then we call it quantum non-Markov state. That is how it has been in the literature. Now, there are some equivalent definitions of quantum Markov state or the equivalent statements. So first is the conditional mutual information being equal to 0. This is same as saying that there exists a universal recovery map, which is a quantum channel that takes B to BC such that even if in this tripartite state rho A, B, C, we lose system C, that is, you just have rho AB, you can still recover rho ABC perfectly by the action of this channel. Okay, so this channel does not depend on this channel, it does not depend on this tripartite state rho ABC. It only depends on rho BC, and that is why we are calling it as universal recovery map. Yes. Uh, there are generalization, but there can be multiple generalization because the this mutual information in multipartite setting, there are multiple definitions, like definitions for it. In classical case, they all will become equal. However, for quantum states, they are be different. So it has to. Okay, so yes, so we are saying that this map is a universal recovery map because it depends only on rho BC. And whenever we act this channel on rho B, which is reduced state of rho BC, then we get back this rho BC. Okay. And it is phase map. So whenever this is equal to 0, so this is something called phase map. It is phase map. Like phase map is an example of this. And then if my state is finite dimensional, that is the dimensions of A, B, and C are finite. In that case, one can show that this tripartite state can be decomposed or written or has this structure. With this is direct sum and this is tensor product and this PIR probabilities. So the Hilbert space of system B can be decomposed as a Hilbert space. Okay, this is direct sum into orthogonal set of spaces. So for each I, these are orthogonal, whereas you can do it as B left and B right. So it can be decomposed in that way. Like this is the product, tensor product here. And then you see here, if you condition on B, then this conditioned on B, A and C are separable. So if you know B, for you A and C are separable. Or if you trace out B. Yes? No, so this is just a notation to say that we can decompose Hilbert space of B in this form. Okay, which I'm like just I said as left and right. However, this is just notation. It's not like left and right as such, but we can decompose this Hilbert space so that some part of system state B will lie in this part and another some part will be lie in this part. And conditioned on B, or if I partial trace B, then A, C will be separable. And if I know B, then A and C are product. And that is why this conditional mutual information is 0. So if I know B, then A and C are product. There is no relation between A and C case. So they lie in such space. There is uh, yeah, maybe it need not be unique. Yeah, so there exists. So I can always decompose it in this way. That is, yeah, maybe. So now we have these three definitions for quantum Markov. So whenever these are equal to 0, these three are equivalent. They are same. Like whether we whatever statement we say, we can derive one from the other. The question come, okay, so we know that, okay, quantum non-Markov state are those for which conditional mutual information is greater than 0. But can we define approximate Markov state? So let's say if this condition is very small, it is close to 0, then we have quantum like approximate Markov state. But that does not hold true for this statement. So my state, so even if conditional mutual information may be very close to 0, the state can be far from the set of all states having this form. In classical approximate Markov chain is still same as if there is yeah, like all this will be equivalent in that case, even for approximate case, but not in quantum. So in quantum, your state can be very far from here, but still have this conditional mutual information being very small. And then it is result of Fuzzy Rayner, like in the recent, like the past decade, there has been multiple developments here. Like if one can say this as a breakthrough result, where it is now understood that the approximate Markov state should be, or it should be like if you can recover your state approximately. So whenever we lose, okay, so this is conditional mutual information. This is always greater than equal to minus log of fidelity. Fidelity is, so if two states have good overlap with each other, then fidelity will be close to 1. If they are sort of orthogonal to each other, then fidelity will be close to 0, like if they are very far from each other. This is how we define fidelity measure. This R is universal recovery map. And so if this is equal to 0, fidelity will be 1. In that case, you can recover your state perfectly, but not otherwise. Now, if fidelity is between this tripartite state and the recovered state is uh, very close to 1, but not exactly 1, or it is close to 1, then you say that your state is approximate Markov state or Markov chain. Yeah. Okay. Yes. No, rho is state representing state of these systems. Yes. Uh, Conditioned on system B. Like, so if I know the state of B, or I have, yeah, if I have B, then I'll be, yeah. So when we say that having B, it means knowing the state of B. For what? There are measured quantities defined which will be different than what this is. Yeah, but there are such. No, we are not about measurements. No, we're talking about measurements. Yes. Yeah, like, hmm. So quantum Markov states have conditional mutual information equal to zero. Quantum non-Markov states have conditional mutual information strictly positive. Now the question or this work is, so when we say that okay, quantum non-Markov state, is it genuine non-Markovianity in the sense the origin of non-Markovianity? If I take convex mixture of states, so let's say if I take states, convex mixture of states which have conditional mutual information equal to zero, I may get state rho ABC. Yeah, so for each of x, conditional mutual information is equal to zero. So for all these states rho x, conditional mutual information is equal to zero. Now, if I take convex mixture of them, then the conditional mutual information need not be zero. Okay, even if conditional mutual information of rho x ABC is zero for all x, that does not guarantee that the conditional mutual information of rho ABC will be equal to zero. Like rho conditional mutual information of AC conditioned on B will be zero. It is not known. It doesn't guarantee that. It can be non-zero. There are examples. So how do we distinguish between classical and quantum origin of quantum non-Markovianity? So in this case, it is like, since we are taking mixture, which we can always do either tossing a coin or through some classical random variable, we can always take this mixture. The non-Markovianity or the quantum non-Markov state that we are creating is from using some classical process, right? And of with quantum Markov states. So how do we distinguish between this classical origin and quantum origin of quantum non-Markovianity? So that is the our main focus. So genuine quantum non-Markovianity in states is non-Markovianity with non-classical origin, and this state, like if they may have conditional mutual information equal to zero, we'll be saying that these are non-Markov state with classical origin. So how do we measure or quantify it? And for this, we propose a quantifier which is defined as, or we call it as the squashed quantum non-Markovianity of an arbitrary state rho ABC. We define it as conditional mutual information. So first, this is a squashed quantum non-Markovianity of state rho ABC. We are looking at correlation between AC conditioned on B, and it is defined as half of conditional mutual information, which is mutual information between AC conditioned on BE. Now, what is this E? So we have tripartite state rho ABC. It can be reduced state of a bigger state. So in which you wouldn't if you don't have access to E, then it will be rho ABC. Okay, so you partial trace E, you should get rho ABC. So you take infimum over all possible such extensions of rho ABC. Need not be pure. It need not be pure. Yeah. And also the dimension of E A priori is unbounded. So in general, it is unbounded. We don't know how to bound the dimension of E. So this is still an open question also for squashed entanglement, which will come. Now, this definition can be said to be motivated from the squashed entanglement, which is a very nice measure in quantum information theory to quantify entanglement between two states, and also upper bound in the key distillation rate. So it also has some operation and has some operational meaning. So the squashed entanglement is a measure which quantifies how much of entanglement is between in a bipartite state between E and C. And it is defined as half of conditional mutual information of all state extensions of rho AC, where is conditioned on conditioning is on extended system. So here F is that extended system, and if you partial trace F from this joint state, you should get back your state rho AC. It is infimum over all this state. This state is known to be faithful for finite dimensional systems. So if rho AC is finite dimensional, then it is equal to 0 if and only if rho AC is separable. Yeah, I mean, interacts. Yes, yes. All the only condition we are imposing here is that if I partial trace E, I should get back rho ABC. And that is what we mean. I'll be meaning by state extension whenever I'll be saying. If I partial trace the extended system, I should get back the original state or the state of my interest. Yeah, it is so it is that it squashes out all the classical correlations, and you are only left with non-classical correlation, which here is entanglement. So that is why they named this as squashed entanglement. And for the similar reason, we name this as squashed quantum non-Markovianity. It is because we are trying to squash out all the classical origin and be left with only the quantum part of it. Yes, yes. And okay, I think it will come later, but one may see. So the squashed quantum non-Markovianity is upper bound on squashed entanglement. If where rho AC is, let's say, partial trace on B here, then this will be lower bound on squashed quantum non-Markovianity. Why? Because here you take infimum over all possible extension of AC, whereas here the structure is saying that okay, you have this B. So it's not infimum over all possible extensions of rho AC, but with some particular structure, and that is why this will be upper bound on this quantity, or this is lower bound. This is lower bound on this. Okay, so now what are the properties of squashed quantum non-Markovianity that we obtained or we show? So we are limiting this proof to finite dimensional systems, even though this quantity is defined for infinite dimensional systems. I mean, same as this. First is convexity. So for any state that can be written as convex mixture of other tripartite states, so it has, yeah, so it satisfies convexity property. By convexity property means this holds. So whenever my state has this convex decomposition, squashed quantum non-Markovianity is of this form, is bounded in this way. Yes. Yes, so in case of pure state, if I take this will be mutual information between AC. So if my rho ABC is pure, then this is mutual half of mutual information between A and C. Yes, squashed quantum non-Markovianity will be between AC. Yes. Uh, yeah, okay, so here, I mean, since B is part of here, but B is not part of here. So, okay, if rho AC is pure, then this will become one Newman entropy of A or C. And same will also hold true here. So if Yeah. Okay, one will have to. It is pure state, so it will be mutual information between ACs. Oh, non-squashed. If we are defining it as conditional mutual information, then yes, in that case. Yeah, so even in that case, which, okay, it will depend which mutual information is more. Yeah, okay. I mean, I haven't computed it, but I'll just say this. So if ABC is pure, then this is equal to half of mutual information. Okay, since it is pure, so let me just write it as this. So it is of this form. And this is also for, it's because, okay, see, this is pure state, right? So you would assume even conditional mutual information to have similar, because there is no, it is not classical mixture. Okay, and if my state is of this form, psi AC tensor whatever, I mean it can be whatever here, then in this case the squashed measure, or if, yeah, it is human entropy. Okay, I don't know whether half will be there or not, but yeah, so it will be one human entropy if B is in tensor with AC. The set of states, yeah, okay. Yes. Oh, yeah, yes, yes. So actually, whenever you take this convex mixture, and if it doesn't have, yeah, some, okay, I mean, yeah, okay, so I have example. So let's say this. Okay, let me write. If so, let us say that these are maximally entangled states. Like we are in qubit system, these are Bell states. So there I'll be like 0 to 3. In this, okay, for each of I, this is highly non-Markovian because conditional mutual the maximum here, right? Conditioned on B, like B has no correlation with AC, and AC are in perfect correlation. Sorry, B has correlation, but if you know B, AC information between A and C is high. So that is there. Right. Now, as quantum Markovianity for this probability will be equal to 0. But the conditional mutual information is not equal to 0. So for this conditional mutual information equal to 0, that is not equal to 0. However, the squared quantum non-Markovianity is equal to 0 here, because there exists this state extension, and one can show that, or one can calculate that the squared quantum non-Markovianity, like with E as that conditional mutual information here will be equal to 0. So it's in that sense. Like there can be also quantum extension which will make it 0. Okay, so now then there is another property which is super additivity, that for every quantum state, rho A prime, B prime, C prime, this condition holds, and this whenever this inequality, so it is called as super additivity property, that property. The equality condition will hold if this state has tensor product form in this way. All ABC, like ABC, one pair, yeah, like in one side and then another tensor product, then this will become equality. So the equality condition holds in this case. It has monogamy property, it is monogamous, the measure, in the sense that for every state rho A prime BC, the squared quantum non-Markovianity. So what this is similar to the monogamy relation for the entanglement. It means that this genuine quantum non-Markovianity you cannot share with many parties. Sorry. It's because, okay, so in entanglement case, like we cannot share entanglement between many parties, right? If two are already, they have high amount of entanglement. So something similar is there. So if genuine quantum non-Markovianity between A prime, C, condition on B is like high, then we cannot have this property being shared with many parties. Like this relation kind of guarantees that, and there will be one example or extendability, like the, what is it called, corollary of this. I'll show it later on, so which should make it clear. And this is called monogamy. If it here, instead of squared quantum non-Markovianity, we can also have squared entanglement. It also satisfies similar property if you ignore B part. But not all entanglement measures are monogamous. However, entanglement itself is. Asymptotic continuity. So any two states, if they are close in trace distance, then the squared quantum non-Markovianity will also be close. Faithfulness. Okay, so yeah, there may be some question here. I'll let you to ask. I won't be saying it myself, if there is. So for any state rho ABC, the squared quantum non-Markovianity is 0 if and only if rho ABC is not genuinely quantum non-Markovian. By that, what we mean is that if there, so this is equal to 0 if and only if there exists a universal recovery map, B taking help of like state extension E, is able to recover rho ABC. So if I partial trace E from here, it will be rho ABC. So this is state extension. Yeah, and this is okay. So for arbitrary pure state, this is half of mutual information between AC. And if pure state is in product form between AC and B, then this is equal to von Neumann entropy. And in both of this, okay, and in this case, it is equal to squared entanglement. Yeah, so consider, okay, now, so these are some like just bounds, like let's say if you were, so consider this set of tripartite state for each of which conditional mutual information is equal to 0. Then there exists a state extension. So this X is a classical register, meaning that all of these states are orthogonal to each other. So this is classical extension. And yeah, so if you are taking classical extension and you are calculating this quantity, then it is always going to be upper bound, because for squared quantum non-Markovianity, we allow for all possible extension, not just the classical extension. But anyway, for this class of state, this is equal to 0, and since this is always non-negative, so this is also equal to 0. So it trivially follows from here. Yeah. Sorry, I didn't get question. No, no, no such restriction. Yeah, so this is like arbitrary. I mean, there is no such restriction. Yeah, it's just that maybe that the sub is like, even if dimension of CA is maybe large. Okay, yeah, no, yeah, that is fine. But sometime at times it may happen that uh, like the non-trivial values, eigenvalues and all, they will be lying in some subspace rather than the full space. Where we like these are arbitrary. So the only condition here we are saying is that this conditional mutual information is equal to 0. And this is what I was saying there on the board. So if we take probabilistic mixture of genuine quantum non-Markov state, they may result in state with vanishing squares quantum non-Markovianity. I mean, which shouldn't be surprising, because even like, let's say, if I take probabilistic mixture of entangled states, we may get separable state, right? So that is fine. So one alternate definition for the genuine quantum non-Markovianity then become that a quantum state rho ABC has genuine quantum non-Markovianity if there is no state extension rho ABC is such that for some universal recovery map. Okay, so here E is missing, pardon. We get rho ABCE by acting recovery map in rho A, and this state extension, if I partial trace E, I should be getting rho A. Yes. Yeah. Yeah, so this is what quantum non-Markovian means. I mean, it is because we had this example here, and if we take classical extension, it would still give us something non-zero. So the quantum, yeah, so yeah, so this is more like by this is so yeah, this is what I was saying. There is subtle. This is more like you are imposing in some way that okay, if this is equal to 0, yes, yes, that will be 0. Oh, yes. Maybe it's because there is this classical extension. So, so let's say, yeah. So there exists this conditioning system, extension, and if I take yeah, so this, yeah, so yeah, yeah, so it will be because in NS, yeah, because in this, so this measure is defined, and this, yeah, so it is state extension. So this will be upper bounded by, if I'm taking state extension X here, which is of a special type. So this will be upper bounded by this quantity I A C B, and now since this is equal to 0, this has to be 0. Yeah, so this is what we have here. So there exists a state extension. There could be different other extensions also, but as since we saw there exists one for which it is equal to 0 and that is infimum, it cannot go further below, so this is fine. Okay. Yeah, so this is regarding that monogamous property. So consider state bipartite state rho AC. We say that rho AC is k extendable in C for all positive integer k greater than equal to 2. If there exists a state extension, which I am denoting here as sigma, A, C1, C2 to Ck, where each of these C are isomorphic to this C, each of Ci are isomorphic to C, such that if I partial trace, okay, beg pardon, I'm missing A here. Okay, so this is sigma A C1 to Ck. If I partial trace all C1 to Ck excluding one of the C, then I should get back the original state rho AC. And this would hold for any I. So I am partial tracing all C except Ci, then I should get back rho AC. Then we say that this state rho AC is K extendable in C. Okay, because there exists state extension of rho AC in which C has K, like there can be C K copies of C. And what do we mean by this? It means that the correlation that A shares with C. So what does state say us? When we are writing rho AC, it means that whatever correlation A is sharing with C, here A is able to share that correlation, exact same correlation that A shares with C, with the K copies of C. Not just one C, but K copies of C, K multiple C. And that is why it is called K extendable. It is extendable in that sense that the correlation that A shares with a party is shareable, exact the same correlation with multiple other parties. And this, if state has this property, any bipartite state or coalition has this property, then it limits genuine quantum non-Markovianity. So for an arbitrary state rho ABC that is K extendable in C, the squashed quantum non-Markovianity is upper bounded by log of minimum of dimension of A or C. So I'm just writing for simplicity here dimension of A divided by K, which is extendability factor. Factor C is K extendable. Yes. Yes. No, that is not possible. So for a maximally state matter, any entangled state is unextendable. Okay, and a state is extendable for a bipartite state is extendable for all k, like k2, 3, 4, like for all k, if and only if state is separable. Okay, and now, okay, I mean we know that I already discussed that the squares entanglement of the reduced state rho AC is upper bounded by the squared quantum non-Markovianity. This relations, okay, so Andreas Winter and Dong Yang, they had shown that squared quantum entanglement for state in which C is K extendable is also upper bounded by this quantity. So ours is sandwiched between this and this. So in that way it is tighter, like, okay. So now we come to the resource theoretic framework. So one can have resource theoretic framework for genuine quantum non-Markovianity. What do you mean by resource theoretic framework? That you define free state, which in our case, which for entanglement theory are separable state. Okay, whereas in our theory it is states with vanishing squashed quantum non-Markovianity. Free operations. So you define free operations. Free operations are those which do not increase or create resource, in which case it is genuine non-Markovianity, and in case of entanglement. So the free operation in entanglement theory should not create or increase entanglement. So first is LOCC operation. So you are allowed to do local or quantum operations and classical communication between AC. Then others are local operation and quantum communication from A to B and C to B, but not the other way around. So local operations on A or C or B, these are included. Like by default, it comes within this definition. And then, so you have free state, free operations, and then you have resource states. So resource states are those with non-vanishing the measure, like resource measure. So in entanglement theory, these would be entangled states, whereas in our case, these are states with strictly positive squashed quantum non-Markovianity. So now we compare our resource theory. So there have been two other works in this resource theory of quantum non-Markovianity in state. So we compare with them. This is conditional mutual information, plain conditional mutual information. This is okay. It is written here. Non-Markovianity of formation. It is motivated from the definition of entanglement of formation. So I won't get into the detail of this, but as you may see that, okay, for the other case, there are some properties which are not holding. These are some of the desirable properties which you would desire from your resource theory. It makes life somewhat comprehensive to understand the kind of correlations you are discussing. Whereas in this case, all are satisfied. I mean, it's just, yeah, comparison, like naive. Okay. So now for the state, so whenever you have resource theoretic framework, you would want to ask question that if you have, okay, so first is you cannot create any resource state from the action of free operations on free states. A resource state can, you can possibly generate resource state if you act resource which is non-free operation on free state. So you can do that, create resource state. Now a maximal genuine non-Markov state, it means that for which the measure is really high, like the highest, is a Bell state. I mean, so I'm writing here bipartite because you can tensor it with any of state with on B, like that is fine. So it is tensor something on B. This is one of the maximal genuine non-Markov state. Now you can prepare any tripartite state. You can prepare any tripartite state that has to be shared between Alice, Bob, and Charlie using protocol like this state redistribution. So I mean, in our case, one can do is what one can do is like depending on what the free operations and all were, that Alice and Charlie, they share a Bell state. So Alice and they are allowed to do LOCC, right? So Alice and Charlie, they share Bell states. So first, Alice locally prepares a tripartite state, rho A prime, A double prime. The goal is how to share rho ABC among ABC and how much resource will they use. Then Alice sends the local state A prime to Bob using noiseless or ideal quantum channel. Okay, so A prime is going to Bob here. And then Alice transfers A double prime to Charlie via teleportation and doing LOCC, I mean, for correction if it needs to be done. And in that case, rho ABC can be generated. So what this is just to say that since this is genuine non-Markov state, so if you use this amount of genuine non-Markov state, you can do state redistribution among ABC. Now consider a state transformation that you want to go from rho ABC to sigma A prime B prime C prime via reversible local operations and perfect quantum communication. Okay, then the quantum cost for this transformation is lower bounded by like how much amount of E bits will you require. This is lower bounded by the difference between their squashed quantum non-Markovianity. Okay, it is not saying here anything much, but so so this is the operation. So we also have, so when in quantum Shannon theory or in Shannon theory, whenever you have a measure, it becomes meaningful if you attach some operational task to them, then it will have operational meaning. In the sense, let's say there is some communication protocol, and if it becomes the optimal rate to do that protocol. So for the case of squashed quantum non-Markovianity, this setup is variant of conditional one-time pad conditional one-time pad, yeah, which gives operational conditional mutual information. So this is variant of that. So the protocol is that Alice wants to share a private message with Charlie in presence of eavesdropper Bob, and Bob has access to a powerful eavesdropper Eve. Okay, so Alice has to communicate to Charlie over noiseless quantum channel, which is identity channel, that is also accessible to Bob. So Bob can look into it, and Bob is eavesdropper. So this is what limits the amount of secret messages that Alice can communicate with Charlie. So if Alice, which is denoted as A, Bob B, Charlie C, share state row A, B, C, and Eve has access to all the remaining systems, which includes the state extension of row ABC, then in the asymptotic case, so on an average, the optimal rate at which Alice can communicate with Charlie is given by twice of squared quantum non-Markovianity. Okay. Uh, yeah, so this is variant of conditional quantum one-time pad where we have allowed Bob to take help of further powerful adversary, sorry, eavesdropper, I mean, it is restricted adversary, who can provide Bob with the system that extends through ABC. So, so this is operational meaning for it. And then another operational meaning comes with the task of state deconstruction. So whenever you have tripartite state row ABC, goal is to decouple A from BC in a particular way. What we are allowed is to perform mixed unitary channel. So yeah, these are unitaries with equal probability, that is, we are allowed to perform this for the task, and you are also allowed to have some ancillary state here. So again, this is in asymptotic limit, so that's why you have n here, like n copies of row. Fine, and this lambda is here. Okay, so we are allowed to this operation upon upon deconstruction of A, the reduced state of row BC should remain asymptotically intact. That is, it shouldn't disturb, which we can measure using fidelity. So fidelity of the reduced state of BC in asymptotic regime should be close to 1. So that is the demand. And then another demand is that it has to asymptotically obey local recoverability condition with respect to B. That is, there should exist a recovery map that when we act on B, we should be getting this here. Okay, I think there is, yeah, we should be getting this. And then the fidelity is again close to 1. Then the question one can ask is, what is minimum number of unitaries required to achieve this successful state deconstruction? Yeah. Yes, so they are related. They are related. I mean, yeah, for now I can only say that they are related. Like it's, yeah, this A, B, and A prime. A, B, and A prime. Uh, this we allow, it can be, okay, I mean, I don't know the bound, but it can be anything. Like this is just ancillary system you are allowed to take. So, yeah, we don't demand. If we are putting condition that the reduced state of BC asymptotically should remain same with the n copies, and if I take partial trace of A here, so whatever I'll be getting, it should be with respect to that. So this is another operational meaning with respect to conditional mutual information. So conditional mutual information comes here as a in optimal rate here. So this Mn is the number of unitaries. So on an average, this is equal to asymptotically, yeah, this is equal to the conditional mutual information. And in our case, what then one can say is that Bob is allowed to have access to, I mean, system E, which extends through ABC, and then in that case, it is twice of squared quantum non-Markovianity, because squashed quantum non-Markovianity is half of conditional mutual information. So it's sort of direct corollary in that sense. If we allow Bob to have this extended system, access to extended system. Okay, so now the conclusions are like for this, the take-home messages are that squashed quantum non-Markovianity is a measure of genuine quantum non-Markovian correlations in quantum states. And for finite dimensional system, it is convex, monogamous, continuous, faithful, and superadditive. For infinite dimensional systems, measures of genuine quantum non-Markovianity based on generalized divergence and probability, like fidelity of recovery and others, one can come up with. We have formulated that as well. I mean, so details are in this. So why it is? Because conditional mutual information can be infinity, right? There is no bound there for infinite dimensional states. Whereas if you have measure with respect to fidelity, or they are always, fidelity is always between 0 to 2. So, and they are well defined also infinite dimensional. The question comes, you have a measure which is well defined always for the infinite systems, then yes, you can come up with that based on these universal recovery maps or recoverability property. And then genuine quantum non-Markovianity is monogamous. So squashed quantum non-Markovianity of an arbitrary tripartite state is always lower bounded by squashed entanglement between non-conditioning systems, and further limited by the extensibility of any of the non-conditioning systems. So framework for a convex resource theory of genuine quantum non-Markovianity is introduced, and resourceful states are those for which squashed quantum non-Markovianity is non-zero. And then we have operational meaning in context of conditional one-time pad and state deconstruction. Yeah. So